Welcome everyone. Today we're taking a look at our introduction to coordinate proofs, and we'll be doing those over the next few days. Today we're just talking about a good way to position the figure, what we call standard position. And so most of our work today is just on drawing the figure and identifying its vertices. And we have just a little bit of the introduction to the coordinate of proofs at the end of the lesson here. So when we're talking about standard position, we're talking about a figure is placed in the standard position when one vertex is at the origin, so 0, 0 is referring to the origin, where the x-axis and the y-axis meet, and the figure is positioned or oriented so that it has as many horizontal and vertical lines as possible. It won't always be the case where we can get every side positioned horizontally and vertically, but we can try. So here's a little bit of an introduction to explain good placement versus bad placement. Let's take an obtuse triangle. Now an obtuse triangle is a bit more challenging just because there are fewer sides that are going to be vertical and horizontal. Here's a horizontal side. Right? There's your obtuse angle. If we were to try to place this triangle on our grid, a bad placement would avoid the origin, meaning if we were to draw this triangle like this, you can see that all three of the vertices are avoiding the origin. So that's not ideal. We really want to try to get at least one of our vertices there. Right? So let's rotate it around, or maybe reflect it around so that it looks like this instead. Right, so again, the challenge with the obtuse triangle is we still don't have very many horizontal and vertical sides. We have one horizontal side, but we like this a little bit better because it puts a vertex of the triangle at the origin, and that means then it's a lot easier to do calculations like distance formula or slope formula at this point because its values are 0, 0. Let's say that the bottom edge of this triangle was something like a length of 4. Well, then we can travel 4 units to the right, and now we know a second coordinate point. This would be located at 4, 0, meaning we've traveled 4 units to the right of the origin, but neither up nor down, so it's right there. Okay. Now, we don't have enough information to establish the third vertex, but this is why we like to put a vertex at the origin, because then we can travel away from the origin to get some additional coordinate points. As opposed to this first figure, even if this is a length of 4, we don't really know what these coordinates are going to be on the bottom of the triangle because we don't know what that distance is away from the origin. So there's too many unknowns that way. So we're going to try and put our figures more like this. So we have a variety of different figures that we're going to work with, and we will be working with examples where we have both values for the lengths of the sides as well as variables for the lengths of the sides. So let's start off with a right triangle. It's a whole lot easier with a right triangle because you know right triangle means that the sides will be perpendicular and the x-axis and the y-axis are perpendicular. So it's very easy to fit our right triangle where the right angle is at the origin. Now it doesn't really matter whether the 2 or the 4 is on the height or the base. In fact, I'll draw it both ways. So here I've positioned my triangle so that the height is 2 and the base is 4. And so what that means is we now know these other coordinates at these vertices. All right, so let's fill this in. Here, if we're starting at the origin and we're traveling to the right, that means we're increasing the value of x, the horizontal distance, the x coordinate. So if we're starting at 0 and we go 4 units to the right, then that means this is 4 units to the right, comma, 0, because we did not travel up or down. So this point is located at 4, 0. Now the top vertex here, it's directly above the origin, so we did not travel to the right, we did not travel to the left, so that x, that horizontal distance is 0. We traveled up 2 units, so that's the y-coordinate. We've increased the y-coordinate. So now we have all 3 vertices identified with ordered pairs. So if we had to calculate the slope or the distance, we have all the numbers we need. All right, so let's abstract that a little bit. What if, I'll tell you what, before I go there, let me just take this back and just real quick just point out that we could have positioned the triangle so that the base was the 2 and the height was the 4, right? So again, it doesn't really matter which way you orient the triangle, because as long as we have our vertex at 0, 0, then we can determine the distance to the right, which is 2, 0, and the distance up, which is 0, 4, right? So either one of those would work just fine. So I'll say this or that is just fine. Okay, now in the case where we don't have numbers, we have variable lengths. We have a leg of length A and a leg of length B. We're not solving for them. We're just going to label them as A and B instead of 2 and 4. And again, it doesn't matter what's on the base and what's on the height. So here is my right triangle. We have 2 different variables, which means we have different lengths, different sizes. So we want to draw the 2 legs different lengths. So I'll put A on the height, and I'll put B on the bottom, the base, and it can be the other way around. So what this means is if we have a vertex at 0, 0, then we can travel to the right a distance of B. So we know this vertex on the right is located at B units to the right, comma, 0. Again, 0 because we're not going up or down. For the vertex at the very top, we're traveling straight up. That means we're not traveling right, we're not traveling left, so the x-coordinate is 0. And then we're traveling A units up, so 0, comma, A. All right, so once again, we'll do just one more variation on this, just to kind of quickly show you that we could have put the triangle the other way, where we had A on the bottom and B on the height. So again, it doesn't really matter which way you do it. Here's our vertex at the origin, 0, 0. And if we travel to the right A units, then that means this is located at A, comma, 0. And if we travel up B units, then this vertex is located at 0, comma, B. So the ordered pairs are going to be different depending on what you label as the sides. So you have to label the sides, and then you have to identify the vertices. Here are some other shapes. Here we have an isosceles right triangle with legs of 6. Okay, so it's a right triangle. And isosceles means that 2 of your legs are the same size. All right, so that means, again, we're going to put that right angle at the vertex. And there are my 2 legs of length 6. So this vertex on the right is 6 units to the right, so 6, comma, 0. And this vertex on the y-axis is straight up, so we're going up 6 units, so that'll be 0, comma, 6. All right, so let's take that same shape, and this time it will have legs of length M. There's my right angle. Don't forget to draw the right angle if your triangle is a right triangle. This is length M. This is length M. So this vertex on the x-axis is M units to the right, comma, 0. And on the y-axis, that is 0, comma, M. All right, let's take a look at a few more shapes. I'm going to turn the page, and we have a few more shapes to take a look at. This time, instead of triangles, we're going to look at some quadrilaterals. Let's start off with the square with sides of length 4. So that's pretty straightforward. We know what a square looks like here. Right, 4 right angles, 4 congruent sides. So that means we have all these vertices to identify. So this vertex in the bottom left, that's at the origin. We're going to go to the one on the bottom right here on the x-axis. This is 4 units to the right. So this is located at 4, comma, 0. The vertex on the y-axis here, we're going up 4 units, so that's 0, comma, 4. And then in the top right corner, we have to travel to the right and up. So from the origin, we go 4 units to the right and then 4 units up. So the x-coordinate is 4 and the y-coordinate is 4. We got them all identified. So let's try that again. This time we'll use sides of length s. Alright, so now we're traveling a distance of length s from the origin. So on the x-axis, we're traveling to the right s units. So this vertex is located at s, 0. On the y-axis, we're traveling up s units. So this is 0, s. And then in the top right corner, to get there, we have to travel to the right and up. So right s units and up s units. So s, s. Let's try a rectangle now. Here we have sides of length 1 and 4. So again, it doesn't really matter what your base is or what your height is. I'll put 1 on the base and 4 on the height, but you could have it the other way around. Let's find all of the vertices. So on the x-axis, I'm traveling a distance of 1 unit to the right, so this is 1, 0. On the y-axis, I'm traveling up 4 units, so 0, 4. In the top right corner, we have to get there by traveling from the origin, 1 unit to the right, and then up 4 units, so 1, 4. So instead of the numbers 1 and 4, what if we had variables, L and W? Again, it doesn't really matter where the L or the W is. I'll put the W on the bottom and the L on the height. There's my right angles. So let's talk about its vertices. So here's your vertex at the origin. Traveling to the right, we're traveling W units to the right. So this vertex is located at W, 0. On the y-axis, we're traveling up L units, so this is 0, L. And then in the top right corner, to get there from the origin, we have to travel to the right W units and then up L units, so we're going W, L. All right, lastly, the parallelogram. This one is the tricky one because we actually need another number thrown in there besides the actual side lengths. So let's start off with a parallelogram that has a base of 3 and a height of 2. So there's my base of 3. We know the parallelogram has 2 pairs of opposite sides that are parallel and congruent. So if the base is 3, then this top side will also be a length of 3. But the slanted side, that is not the height. That is not where the 2 goes. Remember, the height has to be perpendicular to the base. So if we were to extend a little construction line kind of outside of the parallelogram, it forms like this little triangular space. And this right here, that is your height. All right, so that distance of 2, that is the height from the bottom base to the top base. Now we can also draw this on the left-hand side, and we're going to do that here as well. So here's our little triangular space, but now on the left-hand side of the parallelogram, right there along the y-axis. So again, this is your height of 2. Now we still don't have quite enough information. We actually need a third value. And the reason for that is because we want to know how far this vertex in that top left corner, how far is that from the y-axis? And it's actually not given to us, so we're going to make up a number. Let's say that's a distance of 1. Now we're ready to identify all the vertices. So again, at the bottom left, this vertex is at 0, 0. So the vertex to the right of that on the x-axis, this is 3 units to the right. So this is going to be 3, 0. This vertex in the upper left, we're going to the right 1 unit. How do we know that? Well, we had to pick that value earlier. But let's say that's a distance of 1 to the right. So we're going 1 to the right, and then we're going up 2. So this point is located at 1, 2, meaning from the origin we're traveling 1 unit to the right and 2 up. So now, lastly, to get to this last coordinate point on the far right side, we have to travel a distance to the right of 3 units and then 1 more unit. How do we know this is 1? Because we set that distance of 1 on this triangular space earlier. So in other words, 1 plus 3 is the same as 3 plus 1. So to get to that far right-hand side, we add up the 1 and the 3, and that gets us a horizontal distance of 4. And then the vertical height is 2. So with those 3 numbers, the base, the height, and then this little triangular gap, that's really the base of that triangular space, we can find all of the ordered pairs of the vertices. So let's try and do that now with variables. All right, so again, we're starting off with 2 variables, b for base and h for height, but we're going to need a third value to describe this little distance here. So here's my parallelogram. B is for base, so I'll put B on the bottom side and also B on the top side. Again, the slanted side is not the height. The height is always perpendicular to the base. So these are the construction lines here. And so the height is that distance from the top side to the bottom side. And we can draw that triangle in this little empty triangular space next to the y-axis as well. There's the height again. So again, we're missing one piece of information right here. In the previous example, we just called it a distance of 1, just to get some numbers on there. But I don't have a number. I don't have any other letter that they're telling me to use, so we can make up whatever we want. So let's call that a distance of A. So this will be a length of A from the y-axis to that vertex. So now we can identify all of the vertices. So the bottom left, that vertex is at the origin, 0, 0. If we travel b units to the right, we'll get to this vertex on the x-axis, and that is located at b, 0. To get to this vertex in the upper left, we have to go up and to the right. Remember, we always put the horizontal distance first, so we're traveling a units to the right, and then h units up. So it's a, h is the location of that point. And then here on the far top right-hand vertex, this is going to be a horizontal distance of a units to the right, and then b more units. So we want to add them together. Now, they're not like terms, of course, but that is my x-coordinate. You can see how with the numbers, those were like terms. We could add up 1 plus 3 to get that total distance of 4 to the right. So here I'm traveling a, then b, so you add up the a plus the b. And then you're going up a distance of h units. So this looks a little bit odd, of course, but that is your x-coordinate. You're using that comma right there to show you the separation between the x-coordinate and the y-coordinate, that horizontal placement and that vertical placement. So that's the first part of our lesson. We're going to take a look now at the bottom half of this page, which will introduce us to some concepts of coordinate proofs. And we'll do a quick sort of mini example using the square that we have drawn previously. So we'll come back to that in just a moment. So this is really just what we're talking about, coordinate proofs. Let's talk about what they involve and what they do for us and what we can achieve by them. So it says a coordinate proof involves placing geometric figures, like we could place parallelograms, we could place rectangles, whatever. We're going to place geometric figures in a coordinate plane. That means we're going to have coordinates to work with. And we will assign those convenient coordinates to vertices, kind of what we did here, assign those coordinates. Sometimes they're numbers, sometimes they're variables. So what do we do with those coordinates? Well, we can calculate things. We can calculate their midpoints. We can calculate their length using the distance formula. We can even calculate the slopes. And so when you use variables to represent the coordinates of a figure in a coordinate proof, the results are always true for all figures of that type. So this is why we do proofs, to show things are always true. But in order for that to work, we really have to do them with variables. Numbers is just a specific example, but if we use the variable coordinates, then it will always be true for all of that shape. So this is just for your reference. If you forget the midpoint formula, here it is, or the distance formula, here it is, or the slope formula, here it is. And here's our little mini example. So let's use the square that we drew from the top of this page with the sides of length s. So between the two squares, we're not using the one with the numbers. Let's see what it looks like if you happen to have the one with the length of s. And specifically, we're just taking the top side. So if you just kind of zero in on that top side, then we're going to be using this information right here, where the point on the left is at 0, s, and the point on the right is at s, s. I'm going to copy that and draw it down here at the bottom so that we have that for easy reference. So I don't have to keep moving the page up and down. So this is, again, just the top side of the square, which is this segment. The point on the left is at 0, s, and the vertex on the right is s, s. So again, we're not using all four sides of the square. This is the top side only. So if we had a segment, think of it just like a segment, where you had those two endpoints, we can now calculate things. So let's calculate the slope using the slope formula. All right. So it's y's over x's. My slope is, all right, so I have a y coordinate of s and s. So s minus s on the top and x is on the bottom, s and 0, s minus 0. That gives us 0 over s, and 0 divided by anything is 0, which means we have a horizontal slope. I should say we have a 0 slope, which means we have a horizontal line. And yeah, that confirms how we drew it. We did draw it as a horizontal side of the square. What would the midpoint look like? It would visually be right about there, but what would its coordinates be? All right, so here's the midpoint formula. Capital M for midpoint. Let's add up those x's and divide by 2. So we have a 0 and an s. Add up those y coordinates. We have an s and an s. Again, divide by 2. So in the first fraction, 0 plus s is just s divided by 2. And in the second fraction, you have 1s plus 1s, which is 2 s's divided by 2. And 2 over 2 reduces. So what we're saying is we're traveling half of the length of s to the right and a full length up. So that would be the coordinate point right there in the middle. And then lastly, if we ask the question, what would the length be of that side of the square? We can use the distance formula to find that side. We need to subtract those x coordinates. We have an s and a 0. S minus 0 quantity squared plus the y coordinates are s and s. So s minus s quantity squared. S take away 0 is simply s that we need to square. And you subtract the s's and that just turns into a 0. So that'll disappear. So we have the square root of s squared. The square and the square root cancel out, which is a length s. And we already knew it was a length s because that's how we drew the square in the first place. So when we get to the coordinate proofs in the next couple of days, we'll be doing some of these calculations on all the sides, not just the top side, but also the bottom side, the right side, the left side, maybe even with the diagonals. It depends on what the problem is going to ask us to do. But it'll look like this if we have variable coordinates, and in some cases we'll have numbers. But we'll be using these three formulas all the time.